In this video, I'm going to talk about what multiple linear regression is, and I'm also going to go through the basic requirements that need to be met both in setting up your multiple regression, choosing variables, and in checking that your multiple regression met all the assumptions of multiple regression that are necessary at the end. I'm not going to demonstrate on particular software here how it is done. That will be covered in other videos, but I wanted to just talk more from a conceptual perspective about what we need to think about, what we need to do, and what we might need to think about if something doesn't work quite as we'd like to. So in order to do this, let's start off with looking at linear relationships. Multiple linear regression has the word linear in it. That means we're looking for relationships between variables or lines that are linear, line-like. And that's easy to conceptualize when we have simple linear regression, which I have an example of here on the left. And you see that I have my x variable and y variable. I've got a bunch of points that I've plotted for my x and y's. I plot a line through that data, and then of course I have my residuals or errors, which is the vertical distance to the line. And of course it's fit during least squares, using least squares. So that's what's going on here with, simple linear regression. Multilinear regression is quite analogous. It's a little harder to visualize. In this particular case here on the right, I'm including just two x's, two variables. And what you'll see here is everywhere there's a triangle is a point or a circle. I think some of them are circles in 3 dimensions. And this vertical line here doesn't represent error or anything like that. That just is to give an idea of how far it is from the floor here of this cube, okay, to give an idea of what's going on. And so you have this cloud. So imagine a cloud of raindrops or a cloud of points. What we're going to be doing in multiple linear regression, if there are two independent variables, is essentially fitting a plane piece of paper, which is a three-dimensional, or one more dimensional, two-dimensional shape through this three-dimensional cloud, essentially what's going on here. And so you can kind of visualize. Now, if we had more than two independent variables or covariates or whatever you want to call your x's, okay, then it would be even in higher order space that we can't imagine. So we would have the next higher order, dimensional thing equivalent to a plane. And the equation will look quite similar to this. So you're probably familiar with this equation if you're familiar with simple linear regression at all. If you take off this plus epsilon, the e, which represents error at the end, which indicates that the points aren't really going to be right on the line that we fit, you essentially have the equation of a line here. So that part of it is the equation of a line. And that, we've got our intercept and our slope for the line here. Okay, and this just is again to suggest that we're going to not quite fit on that line. Same idea over here. This basically is the equation for a plane. If we take off the plus epsilon, the error term, and we just look at, y equals some intercept plus some, we call this a partial slope, times the x variable, first x variable, another partial slope times the second x variable. And again, this plus epsilon just suggests that the points aren't going to fall right on that plane in most cases. So, and if we go into even higher order space, we'll just have another plus beta times, x, however many we want. We can do however many we want to include in there. Now this is assuming we don't have something called interactions. Interactions will not be covered in this particular video, and that's where things get just a little bit more complex than this. One thing that we want to think about is just the same as with simple linear regression, we can say these partial slopes tell us how much y increases if x increases a certain amount. And so if this first x, maybe this first x represents a GPA or something. Okay, if a GPA goes up by 1 unit, the beta 1 tells us how much our predicted y goes up, assuming everything else is held constant. And the same is true with this beta 2. It says, if this x here, this other variable, maybe this one's a an ACT score, something else, okay? So that ACT score, if that were to go up by 1 unit or 1 point, the beta 2 here tells me how much we would predict the y to go up with everything else held constant, meaning the other x held constant. And again, the epsilon, I guess, indicates that we won't get exactly that value in real life. So it's just our predicted value. If I were to write predicted y here, then I would take off this plus epsilon. You'll often see it written that way. Predicted y is written with just a little caret on top of the y. We call it y hat. Y hat. Once we put in there, then we don't really need the plus epsilon on the other end because the y hat just says it's a predicted y, not the real y. And so we don't have to tell it there'll be some error there. Okay, so that's how different ways we often see the equation. But another way I want you to think about this, other than it being a line or a plane, is that what we have is a constant relationship. What that means is how much y increases when I increase x sub 1 is always the same, and it's always the same no matter where we are in the range of possible x sub 1s. So if we're comparing somebody who has a GPA of 2.5 versus a 3.5, we're going to get the same increase in y, the same increase in y, as if we compare somebody who has a 1.5 versus a 2.5. Wherever we are in that range of x's, a 1 point increase in that x predicts a 1 point increase in y. It's a constant relationship. If that were not the case, we'd have some kind of curve happening. And we don't. Maybe in this situation, we're just talking about multiple linear regression, okay? And the same thing over here if we increase this one. Now, it's also the case that how much y increases as we increase x sub 1 remains constant, not only depending on whatever value x sub 1 is, but depending on whatever value x sub 2 is. There's nothing that messes that relationship up. Okay, so no matter what x sub 2 is, so no matter what your ACT score is, okay, a 1 point increase in your GPA, and that's really a huge increase, so it's probably more realistic to talk about a 0.1 increase, and then we'd multiply this by 10 to make up for it, but we're not going to get that complicated. We'll just say a 1 point increase in your GPA. Okay, so no matter what your ACT score is, a 1 point increase in your GPA predicts a certain size, whatever this value is, increase in whatever our y is over here, okay? That may or may not be reasonable. If it's not reasonable, then we have something going on, an interaction situation going on, where how much this one x affects y depends on what this value is. That is an interaction. It's not something I'm going to talk about more in this video. Just want you to be aware that is something that does exist, okay? Now, we're going to add a third variable here, okay, so that we can think about some things a little more complex. And in order to create it visually, I have to make this third variable binary so that I can show it visually here. It's hard to show anything other than the third variable being categorical if I want to add in a third independent variables. So I'm going to say in this particular case that I have males and females so gender might be my x sub 3 over here. That's my third variable. So I've got GPA, ACT score, and gender over here. And multiple linear regression, if we do not include interactions, assumes that what we are essentially doing in the case that I have a binary variable over here, okay, or multiple categories, is I'm fitting these parallel planes. In other words, I'm fitting one plane for males and one plane for females. But the linear part of it basically says constant relationship, which means these have to be the same distance apart everywhere, these two planes for males and females. So that's another way we might think about or see linear relationships happening if we have no interactions. So what we find again is the difference between the male and female y over here, maybe that's success in college, okay, that y over here does not depend on what x1 and x2 are. it's the same. No matter what the GPA, no matter what the ACT score, the difference between males and females is constant and represented by this beta sub 3 right here. Okay, so that's something to be aware of. Okay, now we can do the same thing if we're talking, instead of males versus females, if we're talking treated group versus control. So we do some kind of experiment, some kind of intervention, something like that. We have one group we call a treatment group, another call a control group. It would work the same way if I have treatment 1 group, treatment 2 group. Okay, I'm comparing these two groups, and if I fit a linear equation here without interactions, I'm assuming that the distance between the treated and the controls is the same everywhere. So in other words, that treatment effect is the same no matter what the value of the x sub 1 and the x sub 2 is here. Okay, no matter what it is, this remains constant. Now, in this case, and in the case of the prior examples I showed you, and in any example, missing covariates can make a treatment effect biased or wrong. In other words, the size of this gap between the two could be wrong if there should be some other variables I should include in the model. Well, there's always the other things that aren't included in the model. If I included in the model here, I've got GPA and ACT score, and this is which treatment group they were in, maybe some kind of a learning intervention. I'm missing gender, I'm missing socioeconomic status, I'm missing all kinds of variables, all kinds of things that I could measure on these people, right? I haven't put everything possible in this multiple regression model, and you never can, no matter how much you put in there, put everything in the model. It's impossible. The question is whether you left out a variable that biases your results, okay? In other words, it makes your results misleading because possibly the variable you left out explains partially why one of these predicts Y the way it does, okay? And if that's the case, we got a problem. So let's say that one of these particular variables here was gender, okay? And I'm saying, and I found a partial slope here that was statistically significant and large. So I'm saying, well, gender predicts this outcome thing. Well, maybe that's not the case. Maybe it just so happens that in your particular study, all the males were older than the females, and it's really age going on. In that case, you've got a missing variable of age that should have been included. It partially explains this relationship between this variable and the Y, and causes bias in the results. The same thing's true if there should be an interaction and you left the interaction out. So essentially this is the same thing. It's similar to as if I did a t-test comparing treated controls, except for I'm also controlling for is the term you often use, or accounting for or adjusting for these other variables that I include in the model. So it's more sophisticated than a t-test. Okay, it gives you better information, and it is a good thing to use when you're treated versus your controls. You couldn't assign them randomly to groups, so they may not be as equivalent as they should. You know, in a good experiment, if you had treated people in one treatment group and another treatment group or a control group, the people in both groups should be similar, okay, in all ways other than the treatment in which they received. And if that's not the case because you couldn't assign them randomly, well, you've got a problem, and because you could end up with one group with more males, you could have one group that's older, you could have one group that has more high-achieving students than others when they are not assigned randomly. It still can happen when it's assigned randomly, but the risk of that is contained in the p-value. Okay, so the p-value already is accounting for that. But it doesn't account for things that are done non-randomly. So if I'm just assigning, you know, like there's an example of a study that was done on milk consumption of elementary school children. Some children got milk with their meal and some didn't, something like that. Okay, I may have the details not quite right. But what ended up happening is the people who were giving out the milk started making sure that the children who, you know, were from lower SES backgrounds and maybe not as well nourished got the milk, and rather than having it be random. It was supposed to be random, but people, you know, cheated. The people cheated handing out the milks because they wanted those kids to get the milk. And so what ended up happening is, okay, the results were what we call biased. They were wrong because the two groups were no longer equivalent. The group that got milk had more of these, kids from challenged backgrounds of various types, lower SES backgrounds in it that may not have got milk at home. So now the groups aren't comparable, and the control group now is maybe from little higher income families. So messes up the findings. And so how would you account for that if that were to happen in real life? If you could put in some variable added to this model, regression model, instead of just doing a t-test then on the milk, non-milk, if you did this regression model and you added in some variable that counts for SES or whatever the factors were that were used to give those kids milk, then it can be helpful in getting down to really what is the effect of milk and what's something that just looks like a difference between the two groups because one group was higher SES than the other group. So it allows us to kind of fix that. So basically, multiple linear regression is a tool that we often use when we couldn't do an experiment with randomization. It allows us to get better results. Do we do it sometimes when we also randomly assign to the groups? Yes, we sometimes do. And that will sometimes make our results even more precise if we were to do that. Okay, so now we got to think about, you've heard me mention variable inclusion. Well, we start off with a theory to create our linear model here. I start off with a theory that some outcome variable, maybe it's success in college measured by freshman GPA, okay, is predicted by combination of high school GPA and ACT score and something else. Let's just say gender to keep it simple here. And that's probably a fairly reasonable model. So how did I come up with that? Well, I've got to use pre-existing theory to come up with that. That often comes from with reviewing literature, just understanding your field very well, really well. I've talked a little about the consequences of excluding or including decisions. They can make those decisions. If I say I decided to do this same model but leave out the ACT piece and just do GPA and gender here, I'm not going to have as accurate a predictions of Y, and I may even have some bias in my partial slopes because maybe there's something that's going on there that needed to be accounted for. So it's really important making those decisions about what to include in your model. Again, we base that generally on theory. That doesn't mean you can put everything in the whole world into the model, because we end up with some problems. One of them is, we call it degrees of freedom problem. It's a statistical issue that just basically says I can't do if there's too many x's in the model, I'm not going to be able to get estimates of my predicted values or my partial slopes and so forth, on mathematical limitations on it, but also it can lead us to some unexpected results. One has to do with something called multicollinearity, which I'll talk about a little bit later. But it also can make some of our other estimates less precise. But the biggest issue really gets down to interpretability. The more variables you have in here, the harder it is to interpret what you've got, to discuss it, to really understand the relationships. And so there's always this trade-off between what we call parsimony, which is the smallest meaningful interpret model that's not missing important things. The trade-off between the short, keeping it short, fewer variables, so it's more explainable, simpler, and more degrees of freedom, which gives us greater power in getting our estimates and our p-value or whatever. And then the other extreme, which is leaving out something that's too important, that's really important. And if we leave out something that's important, again, misinterpretation. So we've got to really think about those things when we make our decisions, and they should be made very carefully, not just on a whim, but very thoughtfully. There are times when a variable is missing because you cannot get it. You cannot measure that particular thing. It's impossible in some way, or it's confidentiality issues. You just can't get that data. Yeah, then you're limited, and you have to acknowledge that as a limitation, and you may have some bias in your results because you did not include it, but it needs to at least be acknowledged that theoretically it should be there and you could not get it there. Okay. Now let's talk about the particular variables. The dependent variable, the Y, okay, has one major requirement. It must be interval ratio. It absolutely must. Can't be categorical. Must be interval ratio. and to do a multiple linear regression. Now, if that's not the case, they have other options. If we have two-level, nominal, or ordinal, we do logistic regression. That basically means binary, something like your dependent variable is a yes, no. Maybe they succeeded at something or they failed at something. They graduated or didn't graduate. That would be an example of a binary or two-level nominal or ordinal variable. And if that was the case, we do something called logistic regression, which has some similarities to multiple linear regression, but is not the same. And it's a little bit more advanced, a step more advanced. So that's something that you would want to do if your dependent variable, again, is like a yes-no type situation, just categories, and there's two categories that can fit into it. Yeah, and one I come across a lot is whether they graduated or not, or whether they met some threshold of achievement, or whether they continued with enrollment in the next semester, retention, things like that that are yes-no type questions. We'd want this after the dependent variable. We need logistic regression. Now remember, I'm talking about dependent. Independent variable is fine to have it, but a dependent variable is problematic. The next thing is if I have three or more categories, then it's not logistic regression. And we do either ordinal regression or multinomial regression, depending on whether those three levels are ordinal or nominal. And we're not going to talk in detail about any of these here, but that there's some similarities, again, to this multiple linear regression that we're doing, but they're more complicated. Okay. Now, independent variables, you can have really any kind of variables, independent variable, if you know what to do with it. Okay. If it's interval ratio, something like age, something like, a GPA, it's just straightforward use. Just straightforward. Oh, let me go back one here. I didn't mention you could have something that's like a percentage. Okay, so it's like graduation, but instead the Y variables are all different percentage rates, maybe from a whole bunch of universities or something. If that's the case, we do something called beta regression, which is even less common. Okay, so let's come back here. Interval ratio, very easy, straightforward, stick it in the model. Okay, a binary categorical variable, meaning there's only two categories, male, female, graduated or not graduated, any of those kinds of things. It's quite straightforward to stick it in the model. And the best way to do it is to code it as a 0 or a 1. So in other words, like not graduate is 0, graduate is 1, or male 0, female 1, something like that. We want to generally put that as a 0, 1 for the sake of interpretability of our results. When we do this, when we put it as a category 0 versus 1 for this binary group, we call the 0 group often the reference group versus the non-reference group or the other group. Sometimes it's a control versus treatment, could be that, and we control is 0, treatment is 1. And what you need to understand here is when we get our regression results out, when we have our estimates of our partial slopes. The partial slope that goes to this variable will essentially tell you how much higher the ones are than the zeros, okay? So that's what you want to think about in terms of deciding which group's 0 and which group's 1. So if you had a control versus treatment, you'd put the control 0 and treatment 1, because then this regression slope, partial slope that comes out of the estimation, tells you how much higher the treatment groups are than the treated versus the non-treated, everything else, all of the variables being held constant. So if all variables are held constant, the treated group is this much higher or lower than the control group. So if you're thinking in terms of something like, male versus female, what you're going to get out if you put the males as 0 and the females 1 is a partial slope that tells you the females are this much different than the males, or this much higher or lower than the males. And that's how you'll interpret that partial slope right there, okay? If you were to do something like you're looking at issues related to race or ethnicity, it's very common to put, white is 0 because whites in the society in which I live, which is the United States, are typically the dominant group. So in the United States, it would be common in most locales to put 0 for white and 1 for non-white if we just wanted to make a simple comparison between the white and non-white group. What it would mean is that the partial slope that comes out of the estimation tells me how much different, higher or lower, on average, the non-whites are compared to the whites, everything else being held constant. Because these are linear relationships without interactions, it doesn't matter what constant, those are all held at. It should be the same. Okay, it doesn't matter what value everything else is. So if I compare essentially a 1 to a 0, and their variables, every other variable that we measure on them, so like their GPA and their ACT are all equal for those two individuals. So everything's equal for those two individuals except for whether they're a 0 or 1. And then it says in that case, this is how much higher the ones are predicted to be than the zeros. And of course it won't always be exactly that way, and that's why we have residuals or error. Okay, so that's what we do with a binary. Those are the two simplest cases. The next case that we might have is 3 or more categories with either nominal or ordinal variables. Let's check through nominal first. What we're going to do with the nominal variables is we're going to do something called dummy coding into several binary variables. Okay, I'll talk through the example here. Hopefully it'll be helpful in understanding what this is about. Most software does this for you kind of automatically, so you don't actually have to do the dummy coding, but it's not the case that all software does it. So some software, statistical software, will do it for you, okay? And automatically. But when it does it for you automatically, often it makes decisions you might not want to make. Okay, let's say we're starting off, in this example, we've got 3 categories, 3 groups, white, black, and Asian, and I just picked those fairly randomly. And, obviously it leaves out other groups, but we're going to pretend that my sample only has those 3 racial groups, white, black, or Asian, in my place, okay, where I live. Let's just assume that's not the case actually where I live, but we're going to assume that for the moment just for simplicity. If we want the white as the reference group, and we most often will put as the reference group whatever the majority is, or something that's been a baseline from the past, or somebody that you consider baseline, and that may bother some people which group we pick, but it's most often the largest group. Not always, but most often the largest group. You really want to be careful that you make careful decisions about this, because sometimes you can pick a group that's really small by accident. You don't want to do that. If there are 3 whites only in this sample, this could be problematic, okay? So you want to make sure you want it to be a largest group, okay? And then what I'm going to do is I'm essentially going to make 2 new variables. One that compares technically the black group to the others, and one that compares the Asian group to the others. But really, as in essence, what ends up happening is the way it's coded is they're each compared to the white group. So we're going to look to see how much different the blacks are from the whites and how much different the Asians are from the whites with respect to whatever our Y variable is. And in order to do that, what I'm going to do is I'm going to create 2 variables, one that compares blacks to whites, and one that compares Asians to whites. And the way I'm going to do that is code the blacks 1, the other 0. And in the for the second variable, I'm going to code the Asians 1 and the non-Asian 0. What ends up happening is I have 2 variables. The white people will always be coded for these 2 variables as 0, 0. That makes them the reference or baseline group, okay? The blacks will be always coded 1, 0, and the Asians 0, 1. Okay, for the 2 variables, okay? And so when I interpret my results, what will end up happening is I will not have any variable that tells me what the whites are. They're really the reference group, so the intercept of the equation is giving you what the whites do, essentially. And if we looked at examples, and examples of multiple regressions will help you see that, but I'm not going to go through numerical examples in this video. It's more theoretical. And then we're going to have one variable that tells me how much different the blacks from the whites, so much higher or lower the blacks are from the whites with respect to the Y, with everything else held constant. And then we have one that does the same for the Asian group. And you need to make sure you've got some in each of these groups here, enough to create estimates. Or if you only have a few, say you only had, 7 in the Asian group, something like that, what would end up happening is your partial slopes would have big standard errors, meaning the p-values would generally be larger. You'd be less likely to find statistical significance, or another way of putting in that, low statistical power in finding out how much the Asian's different from the whites, which is unsurprising, if you don't have very many Asians in the sample, you would have very low statistical power or a hard time determining whether the Asians are different from the whites. And you would only probably see that they are different if that difference is huge. Okay, so that's what we would end up doing here. Essentially, however many categories you have to start with, you're going to have one less than that in terms of your number of dummy-coded new variables that you use. So 3 categories, I'll end up with 2 dummy-coded variables, because essentially the third group is just the reference. And their estimated mean, what they're going to do is actually part of the intercept. Okay. So what if we had 5 groups here, then I would end up with 4 dummy-coded variables, and so forth. Okay, so that's what ends up happening. Now, the hardest thing to deal with really is the ordinal variables in a way. You have to treat them either as nominal or as interval ratio. So if you treat it as nominal, the most common thing would be to take the lowest category and treat that as your reference group, but that can be problematic. And let's take it as an example that your ordinal variable you have, again, ordinal is where you have categories, but the order of those categories means something. Let's say that ordinal variable is level of education. And let's say in the United States, a common way that it might be done is the lowest category would be did not graduate from high school. Okay. The next category would be graduate from high school, but nothing more. The next category might be some college. The next category might graduate with a bachelor's degree. And the next category beyond that might be some postgraduate education or something like that. That would be a common way to do it. If you take, by default, most software will take the first listed category, or the lowest, one that's coded the lowest. So if you go in and if your data is coded as 0 is, or it's more commonly starts at 1, so we'll start with 1. 1 is your didn't graduate high school, 2 graduated high school, 3 some college, 4 bachelor's degree, 5 postgraduate education. If it's coded that way, by default, it will probably try to compare everybody to the reference group of did not graduate from high school because it was coded with the lowest value. That can be problematic because, at least here in the United States, that is a very small group. There won't be a whole lot of people. It'll probably be my smallest group of all, in fact. And so often software has various options and things to let you choose differently which one of those is going to be the reference group. Or you can code it yourself, making your own variables like I've shown you here. In this case, if I had 5 categories, again, I'd have 4 reference variables, and maybe I want my reference group to be graduated from high school, really the second group. And I'm going to compare everybody to that. So there wouldn't be a variable I created for graduated from high school. That would be the default. I would have one variable that's didn't graduate high school, so those few people would have a 1 for that variable, and everybody else in the data set would have a 0. I would have a variable that was for some college, and so those individuals who had some college would get 1s and everyone else 0. I'd have a variable for college graduate and for postgraduate the same way. And then when I got my partial slopes back, my partial slopes would essentially tell me how much each of those groups differed from those who graduated high school only, without some college and so forth. So we compare the not graduate high school to them, as well as those who did more than graduate high school, back to the graduates from high school. So you don't always want to do it in that order. So that's a possibility. Anyway, with ordinal variables, again, we can just treat them as nominal, make those same kinds of comparisons we would make with nominal variables. The other option is to treat them as interval ratio. And sometimes we can do that when it's really a reasonable thing to do. Let's say that your categorical variable, your ordinal categorical variable was income. And you had your incomes divided like this. First group was 0 to 15,000, next is 15 to 30,000, next is 30 to 45,000, next is 45 to 60,000. You can see those are equally spaced, right? So it's quite reasonable in that case to just say that the 1, 2, 3, 4, 5 that corresponds to those groups is very reasonable, because in fact you could figure out a mathematical equation to relate the midpoint of each of those ranges to the 1, 2, 3, 4, 5, how they're coded. It would make sense. Okay, it would be a reasonable thing to do to code them as interval ratio. Okay, and sometimes it's done with Likert type data, Likert scale type data, strongly disagree to strongly agree scales, or it's 1 to 5. However, it would be very odd to treat that as a dependent variable, just one Likert type item. And if I did, I'd probably treat it as nominal myself, but rather than interval ratio. But there are times when, again, it makes sense to treat those ordinal categories as if they were interval ratio. And what has to make sense is that the distance between each of the categories, the ordinal categories, has equal meaning. Like with that salary example, because they were all a range of 15,000, the distance between each category, the difference between the middle of each category, you could think of it that way, was constant. So it makes sense in that case to do it. But there are other cases it wouldn't make sense to do it at all. It wouldn't make sense. I'm trying to think of something else where it wouldn't make sense. But something where the gaps between from one to the next category are not constant. Well, for example, the first one I gave with highest level of education. Does it really make sense to say the gap from no high school to high school is the same as the gap from high school to some college? Like, what are you conceptually thinking of as the thing that has constant difference between those categories? So it probably wouldn't make sense in that particular case. So that's something to be aware of as you think about your independent variables. The next thing to be aware of is with your independent variables, the observations must be independent of each other. Ideally, a random sample. Very often that doesn't happen. But what you want is you don't want some of the individuals within your sample to be more related to each other than others. For example, if we're dealing with data I've collected from a school, if I have students come from several classrooms, and so they're grouped. So I have, so many students from each of, 20 different classrooms. Those within a classroom are more similar to each other, had similar instruction more to each other than those in another classroom. And so when we've got these clusters of grouping, if it is something that could impact the dependent variable, then we have to account for it in our statistical model. We use something called multi-level or hierarchical modeling. It's more complex, okay, much more complex. But it is something that can be done, that exists. Another thing is what we call autocorrelated. That is basically like if you think of your observations being in rows in your data set, if that row order has a significant meaning, like it's time, like I had 365 measurements for this year, day 1, day 2, day 3, day 4, day 5. These are what we call autocorrelated. The value today is strongly related to the value yesterday. The value tomorrow is strongly related day to day. And so when we've got this kind of thing, we have to do something more advanced called time series that takes that into account, and that's not a part of this video either. Okay, some things to think about when you're collecting data for your multiple linear regression. Once you've decided on your variables and so forth, random sample of who or what. Whoever you have a random sample of, that's the people you can make generalizations back to. That's the strict interpretation. The looser interpretation that very often comes up in the social sciences is, well, I can really get a random sample, but my group is similar to a representative of a larger group. If you have some justification for believing that my group is very representative of some larger group, it's not random, but they are representative. You can say, well, this is, I can make generalizations here cautiously. And that's what ends up happening more often. But they need to be made, of course, more cautiously because we don't know for sure that they're perfectly representative. We just are making the assumption that they're representative. And so we may have, there may be something, those who were chosen to be part of our data collection may be somehow different than those who are not. okay, or who volunteered. This would be an example of somebody, if people volunteered to be part of your study, those who volunteered may be different than those who didn't volunteer. So if we think that they're similar to all people in the population of interest, we could be wrong. Okay. Next thing, sample size. Generally, the simple guideline is 10 to 20 times the number of independent variables at least. The more the better, to a degree. You don't want to get to the point that you're making a study more costly or expensive than you need to by collecting more data than you need to. But that's the general minimum you want, is 10 to 20 times. So if you have 5 independent variables, 50 to 100, okay, as a general minimum. You can get more detail about exactly what you need in your case based on what you want to find out using something called power analysis software. It's much more complex to do, but it takes into account things like, the variability or standard deviation variance in the data. It takes into account, what size of effect, we call it, you are hoping to find. Or in other words, say if there's a difference between the males and females, how big does that difference have to be for me to care about it? I mean, if you're talking about a difference, say, in JPA between males and females that's 0.001, you don't really care, even if that's a true difference in the population, right? It's called not practically significant. So, in that case, it's not important to you, but how big does it need to be before it's important to you? It takes into account all those things, quite complex. Okay, so that's something to be aware of. The other thing is if you have more complex sampling, which again, that nest clustered structure, that's much more complex. Or if you're doing something called sampling weights, where you have certain individuals are represented of so many other in the population, that's something more complex, much more than we're doing here. We're going to make the assumption that you're dealing with, you make sure that you've hit at least these requirements here, and you're dealing with a group that is either a random sample of who you may want to make inferences about, or at least representative of them well enough that you can make cautious inferences. Okay, so what we learned from it, partial slopes. I've been mentioning that term. It's basically how much y is predicted to increase if that x increases 1 unit with all of the variables at the baseline, which is 0. Mathematically, that what happens, but because these are linear equations, it's assumed that this is the case no matter what value the others are, okay? So this is my predicted y, whatever this value is. It equals, maybe it's maybe it's a college GPA or something. It's 2.15, that's my intercept, plus this much times this value, this much times this value, minus this much times this value. Those are just made up numbers. They don't represent anything real, so it's hard to talk about in real terms. But in each case, in this case, this 0.31 basically, well, the 2.15, let me start off with, tells you what happens if all these variables are exactly 0. Okay? Sometimes these variables cannot be, or practically speaking, never are 0. That's very commonly the case, which makes this not really an interpretable number. Some people like to get around that by what they call centering a variable. So for example, if I had GPA as this variable here, instead of putting in as the column of data for everyone GPA, I would take GPA minus the average GPA of everybody. And if I did that for each of these 3 variables, if I centered them all, meaning for each of these, instead of putting in the actual data for that variable, I did that data minus that variable's mean, what I end up having is a column of how much each of these are different from the mean. So person 1, what they have for x1 is how much they are different from the mean of this variable. And what they have for in the x2 column is how much they're different from the mean in that column. Could be positive or negative depending on their higher or lower, and so forth. If that's the case, then this tells me the predicted y if all of these are essentially at the mean. So sometimes that is a very practical thing to do. But we'll assume we're not at the moment to talk about it more simply. We're just saying basically here, if I have increased now my x1 by 1 unit, I expect my y prediction to increase by 0.31 units. If assuming these are held constant at any value, it doesn't matter what value. In other words, comparing 2 people, one who has a higher x1 than the other, okay, by 1 unit, if this x2 and x3 are exactly the same for those 2 individuals, okay, then the person who is 1 unit higher on the x1 will be 0.31 higher on the predicted y. okay? No matter what the values are, so long as they're the same for the two people who are different by 1 here, okay? That's essentially what all this is trying to tell us with this linear model. So it gives us a predicted value, okay? We want to be careful of our language. Sometimes people will use correlation language when we're talking about linear regression, but we're not really looking to see what variables correlate with each other. We're looking to see whether variables predict, whether a group of x's predicts a y, not correlates with. So that's just more precise, okay? We're not looking to see whether something causes, not looking to see whether, you know, increases in this cause an increase in this. You might come to a reasonable conclusion in your head that it's the case, but you would need quite a bit of evidence of different kinds, which is a whole different topic. We could talk about it, like what could strengthen that case. I mean, it doesn't rule out causation, let's say. You find that, you know, higher GPA in high school predicts higher GPA in college. It doesn't rule out causation, but technically it's not really a high school GPA that's causing them to succeed in college, right? It's what they learned in high school, or their academic abilities in some way, or how much they study. You don't know. So we gotta be careful about language. We don't use cause, we use predicts. Here's the things we need to check. Regression assumptions. So basically, these are the things that if we have done correctly, all of our partial slopes and our p-values and confidence intervals on those partial slopes will be as accurate as possible if all these requirements are met. The first requirement is actually linearity, that is the case, as we've discussed it, okay? So the relationship between really any x and the y is linear. Essentially what it really means is there's those constant relationships. It doesn't matter what value of you know, x is or what value of the other x is, you know, in terms of there's always a constant relationship between a particular x and y, no matter what the values of anything else are in the equation. The other thing we want to make sure of is no influential outliers. A lot of people talk about outliers. You probably have a vision in your head for what they are. Those are things that are way outside. When we fit a line, a simple linear regression case, you know, way outside the line. If you imagine, you know, 2 predictors in a y, then we have a cloud of points, 3 dimensions here. There's essentially 3 variables, including the y. You know, one that's way far away from the cloud, okay? But we don't just care that it's far away. We care that it's far enough away in a direction that it changes our estimates, okay? It changes those partial slope estimates because that point is there. More likely to happen in a smaller sample. Once you get samples over 100, it's less likely for this to happen. That essentially, the larger your sample is, the bigger an outlier needs to be, or the further it needs to be from the other points in order for it to have influence and really change our results, okay? The other thing is something called homoscedasticity. Essentially what this means is my prediction is just as good for low values of any x as for higher values of any x. Okay, that's what it essentially means. Otherwise, we have some problem there. Normality of the residuals. The residuals are, again, the difference between an actual y value and what was predicted from the equation. If we were to find those for every individual in our data set, those residuals, that should have a normal distribution in order for our p-values confidence intervals to be accurate. No multilinearity, that basically means that we don't have 2 x variables that are measuring the same thing or very close to the same thing, or that we don't have one variable, x variable, that is like a linear combination of, so maybe the sum of 2 of the other x variables, something like that. And we have problems if those things happen. I'll talk about the problems in a minute. First, I'm going to tell you how we check these things. Linearity, we most often look at with plots. These are the simple tests. There are some statistical tests, some more advanced tests, but most of these, except the last one, are plots. Okay, what we most often do with multiple linear regression, because I have so many x's to look at, there'd be so many relationships to look at if I did plots of everything 2 at a time. So what we most often look at is a plot of the residuals versus what we call either the fitted or predicted plot. What that basically means is on the x-axis is my fitted or predicted value. That means my predicted y, the y that is predicted from the equation, and the residuals, or how far that was off with my actual data set. I look at a plot of that, and I should have no significant, obvious, clear curves, clear and obvious curves. I should have no influential outliers. And again, I look at that same plot, and I don't want to see any really extreme points outside, that are far away from the others on that plot. Homoscedasticity, I look at that same plot, and what I will see, I don't want what's called a funnel or cone shape, which means essentially if I look at that plot, I don't see from left to right or right to left. It starts at, close to the line, close to the middle, and spreads out like a cone or funnel. Don't want that particular shape. I want normality of residuals. I look at a histogram, generally bell-shaped, doesn't have to be perfect, but the more perfect it is, the better your p-values and confidence intervals are. Multicollinearity, that is a little different one. All of these other ones you have to also look at with simple linear regression. This is the only one you'd have to look at with multiple linear regression. That is because multiple linear regression has more than one x while the others don't. Really, it's an issue of too strong a relationship among the x's themselves. Either one is very similar, or to another, one variable is very similar to another, or it's very similar to a combination, some linear or additive combination of some of the others. And this is best found using statistical procedures. I generally look at something called the variance inflation factor, which most statistical softwares will give you, and I want that to be less than 4 for every variable. That's what I generally want. If it gets to around 4 or higher, then I may have a problem with multicollinearity. Let's talk about the problems if any of these things happen next. If I don't have linearity, bias in the partial slopes. The partial slopes aren't as good. The real issue underlying it is the predicted values aren't as good as you would be able to get if you fit a more appropriate shape than aligned to this data. So if you imagine just simple linear regression, if it was really a curved shape and you fit a line through it, you are not going to be predicting your y as well as if you actually fit a curve through the data. Okay, influential outliers. Same thing, I can have my partial slopes be off because it's like pulled the line or the plane or the higher dimensional shape that we can't imagine the wrong direction, too far one direction. It's changed our partial slopes from what they should be, and my predicted values, of course, would be off as well. So that's a problem there. Okay, so I have problems with these partial slopes not being the best they could be in these cases. The other cases here, we're going to be more concerned about the p-values and confidence intervals being inaccurate. If I have heteroscedasticity, which is, again, essentially, if you imagine a line, simple linear regression, the points are closer to the line at one end than at the other end. Okay, if you can imagine, that would make kind of a triangle shape. We call it often a cone or funnel, and we can see that more clearly usually with the residuals versus fitted plots, but you can with a simple linear regression see it just plotting x versus y. If that's the case, my p-values and confidence intervals are fairly misleading because really I should have better p-values for certain values of x than for others, but it just gives me one p-value, so it's kind of misleading. Okay, non-normality of the residuals, so they don't fit. A histogram of the residuals does not look at all normal shaped. That most often the problem is that it's extremely, extremely skewed. Inaccurate p-values and confidence intervals again. Multicollinearity, we basically end up with standard errors that are too big, which basically leads to, again, inaccurate p-values and confidence intervals as well. What ends up happening is it's sort of like, if you imagine that for 2x's, when you had Fahrenheit temperature and when you had Celsius temperature, you can't estimate a partial slope perfectly for both of those simultaneously because they're really the same thing. And so it looks often like neither of those. It's like kind of like it's splitting how well it predicts the y from each of those. So neither of them look like they're doing very well. And the solution is to take out one of them. Okay, so which is what we come to our solutions. If I don't have linearity, if that's a clear lack of linearity, you generally have to transform one of the individual variables, which means like take the logarithm of one of the variables. Very often it's the y you need to take the logarithm of, but not always. You may need to square a variable, you may need to take a square root, you may need a variable cubed. There are a lot of guidelines online as to what to do with that, but most often the thing that will fix that is a logarithm of a variable. The problem with it is your interpretability changes. It becomes impact. impacted by that. Influential outliers, you may try removing them, or something called Windsorizing, which Windsorizing means like bring it down to a level that's reasonable. So if your problem was you had an outlier because the age of one respondent to your survey was 95 years old, everybody else is in the 20s to 60s, okay? One thing you could do called Windsorizing is to take that 95 and bring it down to the next highest value, maybe it's age 65. Bring it down so you don't lose that data point altogether, but you bring it to a value that it won't have so much influence. So again, that's one thing that might be helpful. Heteroskedasticity, often the transforming individual variables, just like we did up here, can solve this problem. Sometimes it's the result of having missing variables that ought to have been included. Non-normality of residuals, transforming variables can be done here. There's also some other more advanced solutions to that, okay? And with multicollinearity, you just want to leave out one of the variables that you think is causing the problem and retest. And that's it for this video.